Please do confirm once that I am audible and the voice is coming. There is no echo and you can see me, you can hear me.
Voice audible, but some clarity is not there, sir.
Okay. Is it clear now or still the same thing is there?
Yeah, it's okay, sir. Now.
Okay. Echo is not there, right?
Yeah, I think it's called a room echo. It's little bit sound, resound is coming.
Oh, okay. The only
That
condition
we
which,
can't avoid it.
yeah, it cannot be avoided. Only condition which should be met is you, I should be audible to you. Quality of the sound does not matter much. Okay, let us start. Just like what we have done in the previous session, I'll be giving you some of the ideas regarding the concepts which were there in this week. Then we will be solving 10 MCQs. Okay. Please keep a notebook and pen handy. Okay. And do try to note down some of the things. After the class is over, please take the PDF and just try to see what are the things which we have covered. Okay. So thereby you will get a very good idea that how you have to solve, what is the approach which you have to take. In the previous in the previous lecture, we have just covered the various statistical analysis which can be used for calculating different parameters related to reliability analysis, mainly your time to failure, mainly mean time to failure, as well as the exact reliability in series and parallel combination we have tried to calculate. And we have just tried to discuss that what are the different types of configurations which are possible in various of the industrial uh, setups. Okay. So with keeping the same spirit, we will just like to go through, delve through some of the concepts, okay, which have been covered in week 3. Okay, and let us begin. Okay, if at any point of time in the previous session or in the present session or regarding this course you have any sort of doubts, feel free to ask. Let us move forward. Yeah. So I have prepared this particular handout, okay, for you to just revise some of the concepts. Okay. Try to see here mathematical foundations have been displayed here of continuous lifetimes. So lifetime or your time to failure, TTF. Okay. It's modeled as a continuous random variable. Okay. It's a continuous random variable. Means, first of all, for the entire domain in which x has is there, the f of x should be defined. It is continuous. It is random. Okay, continuous is there means in the entire domain from minus infinity of x to plus infinity of x, it should be defined. Okay. Random variable with capital T greater than equal to 0. Okay, because failures cannot occur prior to operation. The probability space is restricted to T belongs to open interval, closed interval, 0 means 0 can be there. Component A, instantaneously failed. Okay, at 0th hour it can also fail, but at infinity also it can fail. Means you are not able to calculate after how much time it will fail. So failures cannot occur prior to the operation. The probability space is restricted to t belongs to closed interval 0, but open interval infinity. Okay. That is the thing here. The random variable capital T is governed by the PDF, probability density function f of t, and cumulative distribution function CDF capital F of t. Okay. PDF in case of probability density function non-negative t is there, means it should be positive. So value should be greater than equal to 0. Total probability is equal to 1 from when you will just integrate it from 0 to infinity. Okay. Do try to remember it is 0 to infinity. In my previous of the lectures, previous of the courses, I have seen in the examination some of the students instead of 0 to infinity, what they do 0 to 1, and they try to integrate, and after it is not coming to 1, they just write like this and say, sir, it is coming to 1. So it will not help. Okay? We have to integrate from 0 to infinity. That is the problem. This I have observed while checking the notebooks of the previous semester courses. So for this, what has come to my mind. So already I have told you that you have to integrate for the total probability. Means T in totality should be covered, then only the entire sum. Okay, area under the curve will come as 1. Now you see CDF function is there, means cumulative distribution function is there, capital F of 2. It is nothing but probability of capital T less than equal to T. Okay. Capital T, small t, already we have defined. Okay. Just have to integrate using the your probability density function that has been given to you. F of u du. Already we have just tried to solve one of the questions in the previous session, if you do remember. Okay, we already have solved one of the question based on this. Then your expected value, mean time to failure, MTTF, you just try to calculate as the expected value of the lifetime variable, capital T. It is nothing but 0 to infinity t into f t into dt. Where in place of t you can write f of u, then you have to write u f of u du. Okay, so it's a general perception here. Yeah, one question is there. So for probability space, why open interval for 0? If it is always positive, right? Here, no probability of okay. Means if this why open interval for it's twice a bit. I don't think so. It's an open interval. Please see here. T can be 0. It's closed interval. I don't think so. It is open interval. Oh, why this confusion is there? Please elaborate. Unmute yourself. Feel free to ask me. I'll answer all your doubts. Don't worry. Just tell me that where exactly the confusion is there. What exactly are you thinking? It already has been written here. Failures cannot occur prior to operation, but it can occur at 0th second also. So we have tried to include 0. It's not open interval, it is a closed interval here. And it can be 0 and it can be more than 0, greater than 0. That is what I wanted to tell you. Means both 0 to infinity, both the probabilities I am taking into account. That is why I am integrating from 0 to infinity, not excluded 0. Still, if any doubt is there, feel free to ask me. Is it clear? Not clear? We shall move forward. If it is clear, okay. She has just left. Okay, no problem. No, Gayatri is not there. Okay. Later on, when she'll join, I'll ask once again if she is still having any doubt. Yeah, so I was telling you the expected time to failure. Okay, mean time to failure is nothing but definite integral 0 to infinity t f of t dt. Yes, Gayatri, already you have asked one question. I think your connection was not good, so you were logged off. The probability space y open interval for 0, it's always positive here. See, failure cannot occur prior to operation. I'm not including the negative values, but I'm including 0 here. See, it's a closed interval. First of all, it is not an open interval. I want to tell you, it's a closed interval. 0 means I'm failure can occur at 0 at second also. Okay, just after infinitesimal operation means at 0.0001 second it can occur. That is why I have included 0. I am not including infinity. And here also
Okay,
I'm
sir. Thank you.
integrating from 0 to infinity. I have taken into account 0. Okay, so it is a
Okay.
closed interval. The failure can occur at 0th interval. Okay. And
Okay.
yeah, it will be positive. Definitely, it will be positive because failure cannot occur prior to a question. That is the case.
Okay, sir. Thank you.
Okay. If any doubt is there, feel free to unmute yourself. When few students have joined, feel free to ask any of the doubt. Okay. Please don't repeat in your mind. Yeah. If you want to prove this particular theorem, then in the entire proof in short, I have written here that mean time to failure for the expected value of capital T is definite integral 0 to infinity RT dt. Okay. So via integration, if you want to solve, then you can place using substitution, you can go for replacing u with respect to t. When du is equal to dt, then you try to calculate dv, which is nothing but f of 2 dt. Then you try to differentiate and integrate, and after that you will get the same value. Okay, same value you will be getting. That definite integral 0 to infinity t into f of t is equal to this particular expression. Okay. Then when you place the lower boundary, upper boundary, and everything, you will get mean time to failure as 0 to infinity RT dt. When you are having your free time, then you can just look for the mathematical proof. Otherwise, you can directly just remember the expression. Totally depends upon you. In theory, also, Madam has greatly covered this particular theorem and she has tried to prove it. So I'm not about repeating it once again. But do remember what is the value mean time to failure. It is nothing but reliability T, RT, and definite integral of that particular value from 0 to infinity that you have to calculate. Already in my previous session also, I just tried to calculate some of the questions. Okay. So we go check them also. Then you go for reliability function, capital RT. Reliability function RT or the survival function gives the probability that a component functions without failure unless until it is time small t. Unless until it is small t and the component should function okay properly. That is the thing. Means probability that this failure time should be greater than small t. That is nothing but 1 minus f of t, where capital F of t is nothing but the reliability. Okay. So directly you will be integrating from t to infinity. Okay. Or if it is given from 0, t is 0, then you will directly integrate from 0 to infinity. Okay. Then the hazard rate h of t is, you can define it from the first principle. Okay. Here it has been extensively covered, but we have seen in the very first lecture that the expression will come small f of t divided by r2. So directly we have just tried to cover it, but here using the first principle, if any confusion is there, for removing your confusion, I have tried to revise it once again. Already we have seen it how it is calculated, so I'm not trying to repeat you that same thing. We will try to solve some of the questions instead. Thereby you will get better idea. Here also it is given that y(RT) is exponential of minus h of t, where t is nothing but the hazard rate function. Hazard rate and reliability, where direct mapping I have provided you. Okay, so you will directly get this particular expression. If anybody is having a doubt, feel free to go through this. Very simple integral is there. You will be directly able to solve it. So in short, for exponential distribution, a PDF would be nothing but lambda e to the power minus lambda t. Okay? Where constant lambda should be a constant means it's the failure rate. Okay, lambda in hours. In per hour means 2 per hour or 3 per hour, that means failure rate should be given to you. So PDF is nothing but f of t is equal to lambda e to the power minus e lambda t. Okay. Then CDF is there, that is nothing but 1 minus f of t, that is 1 minus e to the power minus e lambda t. When RT is the reliability, RT you can define as e to the power minus lambda 2 and hazard rate is 0. Just like the table I gave you in the previous class, only this much remembering is more than sufficient from the examination point of view. Which you can go through it with them. Okay, if any confusion is there that how this particular expression has come, then feel free to go through it. Okay. Now there exists a memoryless property, which we have already seen means the probability that it will fail after a certain interval of time will be independent that how many interval of hours prior to my operation the component has operated. Yeah, that is the physical significance of the memoryless property. Means probability of a component failure in future time window depends only on the window duration small t, not its current age s, means prior to my operation how many number of hours it has already operated, that is not in consideration. In case of your classical bathtub curve, which we have seen in lecture 1, this characterizes the useful life phase where failures are driven by random environmental shocks rather than your physical degradation. Okay. So already a Weevil type of distribution is there in which reliability is defined, then how hazard function is defined. Okay, if for this particular distribution, the reliability function is given here, and in that particular case, P is also there, eta is also there. Okay, all the values are there. Then shape parameter beta analysis is there, means if beta is less than there, one, then it is a case of infant mortality. Means h of t is decreasing over the time. Means three different curves, in three different phases, we have divided the entire bar structure. Okay. And after that, we have tried to categorize that whether beta is less than one, beta is equal to one, or beta is greater than one. Whether it is the case of infant mortality, constant failure rate, or wherever or age involvement. So, in case of your normal distribution when we will use for components exhibiting localized wear out concentrated around mean time mean with variance sigma square. Log normal distribution where we will use a random variable capability is log normally distributed if it is follows the log normal distribution with mean mu and variance sigma square. And mean time to repair and fatigue crack propagation is predicted using standard models. Quality skewness is observed. Then stress strength inference theory is there. Okay. The reliability in stress and mechanical design is modeled as probability the component strength X exceeds the applied stress capital Y. Okay, means X should be greater than Y. That is what we have tried to mathematically formulate, and we have tried to keep a safety margin also, that is x minus y. Okay, mu d is there, then sigma square d, sigma d square is there. This all would be taught to you in mechanical engineering designs. Okay, this is mechanical engineering design course in which you would be taught it in much greater detail. Okay. Here just the expression part and little bit about the classification and everything is there. But when you will be experimentally performing this stress system analysis as well as you will be calculating that what is the exact strength of material, then this particular expressions will come in detail. Yeah, the D, okay, it will try to follow the random variable Z, means Z distribution, it will try to follow. Okay, then the value of Z you can calculate, then probability D is greater than zero. Okay, and design stress is in design strength means the strength should never exceed. It should never exceed the Y means strength should be always greater than or uh, far greater than Y. Means stress should be always less. Otherwise, the component will fail and it will have a tendency to fail with respect to time. That is the case here. Then cumulative distribution function phi you can calculate and then probability you can calculate. Then reliability you can calculate. Then reliability, system reliability for small n components and independent components. If it is in series, you have to multiply. That is the case here. Pi is product, you must be knowing. Sigma is summation. Then system reliability, yeah, in case we already have defined then exponential of minus which system individual component reliability we will calculate and then we'll try to multiply out well. Then taking the natural laws and everything differentiating everything is lower. In case of parallel components, how you will do? Okay, you will be calculating 1 minus product of 1 minus RIT, where RIT is maybe the individual system reliabilities. Okay. Then derivation of the mean time to failure equations for n component series versus n parallel series. So this all derivation in MPPF for parallel and as well as series components. I just tried to define here. Okay. For series, it would be 1 upon n lambda, whereas for parallel, it would be 1 minus e to the power minus e1 by t whole raised to power n. Already we have seen through various examples, but still, since the expression I have tried to define using the first principles, so that is why I'm defining it here. Okay. And mean time to failure in case of parallel configurations will follow harmonic distribution. This you try to remember. You take harmonic distribution here and then you try to calculate. You will see some of the examples. Using this particular expression only, we will be trying to solve some of the examples. Okay, then you will have the better clarity how you can solve the questions in the examination. Right. Don't worry much. I'm just trying to show you some of the questions. Comparison and architectural insights in case of your failure conditions, or in case of your series system, it fails the first component, okay, and parallel system, it fails, the entire system is declared to fail when the last of the component fails. Reliability RT expression is there, okay, different cases. MTTF expression is there, okay, HN here is the harmonic mean, okay, and it has to be divided with respect to the lambda, okay. So we will see some of the examples. Then system lifetime distribution is exponential. In series, in case of parallel, it is non-exponential. Scaling behavior, uh, it's inversely proportional in series system, and it is logarithmic growth, okay, in case of your parallel system. Okay. Then series degradation, you can see here. In parallel diminishing, you can just try to see that for which number of components, how the harmonic series is progressing. Based on that, only some of the points we have tried to reduce here. Then yes, system reliability, we have tried to declare it. In hazard function, we have tried to define in all the perspective cases, we have tried to calculate hazard rate ratio also. Feel free to go through these proofs. Okay, if at any point you have missed something that you are not able to recall, that how in particularly a particular expression or in particular expression is being defined. So feel free to go through these proofs. It follows a memory-less property constant failure rate lambda, and the parallel system exhibits a time-dependent increasing failure rate or aging behavior. If you will go through it, as well as in case of your parallel system, it's a nice project. If you are planning to take it in your BTech or technical project, you can always go through system modeling. You can always take it as a BTech or master's project in which you try to model the reliability or hazard rate of a series or parallel configuration. In this particular this web page, I have just tried to plot a particular code. I have taken this particular hazard function. This particular hazard function I have taken for your series as well as your in particularly for your parallel configuration. And with respect to my n, with respect to my time, how my system hazard is progressing with respect to my lambda and with respect to my. So this I have tried to make it as a plot, and I have tried to show you that with respect to lambda equal to 0.05, lambda equal to 0.1, lambda equal to 0.18, 0.2, how my this particular hazard rate h of t is given. Okay. So this type of project you can take in which you try to model the hazard rate function with respect to technique. As well as it is very crucial in cases where multiple number of components are required to function either in parallel or in series. For example, in case of your nuclear reactors. Okay, in those particular cases, this system reliability is very important. So using those real-time parameters also, if you are planning for some research, you can model a particular GUI, graphic user interface. You can model this type of graphic user interface in which you can see that how these particular type of operations are getting performed. So this is the entire functionality which you can see. You can take it as a bit of a Amiga project. Now we'll try to go through some of the concepts. Okay. Here also keep a notebook and pen handy. I'll give you 5 solid minutes. Please go through the question first. Okay. Try to jot down what are the variables that have been given in the question. So after that, try to recall which is the concept which you can apply. And if you are able to solve, then feel free to comment your answer in the chat box. Otherwise, don't worry, I'll solve stepwise in front of you. After this particular session is over, please take the PDF, take the video, okay, and wherever you are having any doubt, feel free to go through it. And once for once and once here and once before the examination, twice at least, you just try to solve each of the problems. That is the sincere request. Okay. Let us look through our first problem. See here, components time to failure. Capital T follows a particular PDF. Okay. Components time to failure. Take the red pen. Yeah. Components time to failure. Time to failure is capital T. It follows a continuous distribution. Okay. It follows a continuous distribution with probability density function PDF as f of t is equals to c e to the power minus 0.05 t for t greater than equal to 0 and 0 otherwise means for all the values means from minus infinity to 0 both are non-inclusive it's 0. Okay. Find the normalizing constant c, that is the question. Okay, then calculate the reliability of the component at 10 hours means capital R 10 you have to calculate. First of all you have to calculate c, then you have to calculate R. Try it. Which property you will use, first of all remember that. After that you just try to solve. Just 1 second. Yeah. Take notebook and pen. Go try to note down what are the values, what have been given. Okay. After that, do try to solve this particular question. It is a very simple question. Okay. But at least note down all the values. After that, we'll see the solution if you are not able to solve. Okay, no problem with that. Here, we'll try to see here, no problem. In this particular case, if you will try to see what I have told you, that if your PDF has been given to you, principal property of PDF, which I showed you in the very first of the page, is what? See here, once again, no problem. Here, PDF, it will be non-negative. First thing is this, then the total probability, definite integral of this particular PDF 0 to t, 0 to infinity f of t dt will be equal to 1 because sum of all the probabilities is equal to 1. Okay. So definite integral 0 to infinity f of t dt equal to 1. So in this particular case, f of t has been given as c multiplied by e to the power minus 0.05 t. So c into definite integral 0 to infinity is e to the power minus 0.05 t dt is equal to 1. Definite integral of e to the power minus x is nothing but e to the power minus x divided by minus x. Okay. So that only I have written here e to the power minus 0.005 t divided by the the exponent, the coefficient of the exponent will come in the denominator. Okay. So that would be minus 0.05. Then putting the values as 0 to infinity. Okay. That c into this particular value is equal to 1. This implies that c into, you try to put infinity first, e to the power minus infinity, what is the value? How the curve of e to the power x looks? E to the power x is like this, or e to the power plus x. Okay. For e to the power minus x, it will be like this. Means e to the power minus infinity will be equal to 0. Yeah. Minus e to the, here you will place 0. Okay. So e to the power 0 is 1. Then 1 upon 0 minus 0.05. Okay. Minus minus will become plus. So c into 1, c will come as 0.05 if you will be solving this particular equation. Okay. C multiplied by 1 upon 0.05 is equal to 1 means c is equal to 0.0. That was my first question. Okay. So C is 0.05. C 0.05 means this can be my option. This can be my option. This won't be correct. This won't be correct. Directly through elimination, I have eliminated two particular options. Okay. Now I will find what is R10. R10 means reliability after of the component after 10 hours of usage. Okay. That will be nothing but this probability that time to failure is greater than 10. Okay, so I'll integrate this particular reliability function because see, I have already calculated then RT, I can write it down as 0.05 multiplied by e to the power minus 0.05 t. Okay, so definite integral of this particular value from 10 to infinity, if you will try to calculate, then it will come 0. Definite integral 10 to infinity 0.05 into e to the power minus 0.05 t into. Okay. So R10, if I'll try to calculate, I'll try to put this particular values. So e to the power minus x dx, that integral is e to the power minus x divided by minus x. Already told you, you try to put 10, then you try to put infinity. E to the power minus infinity is 0. And when you will directly substituting 5 here, okay, so it would be e to the power minus 0.5. So 1 upon e to the power 0.5 will be nothing but 0.606. Okay. So that would be my R then. Okay. If it is coming as 0.606 in option number 3, means A would be my correct option, this would be the. What is the physical reliability? Physical significance means if f of t, I'll try to plot it. It will be having plot some like somewhat like this because the plot is exponential of minus x. Okay. Generally, this particular one is f of x equal to e to the power plus x. This one is e to the power minus x. So it would be having plot somewhat like this only. Okay. So valid probability function must account for all possible outcomes. Means the total area in the f of t should be exactly equal to 100%. Now, from 10 to infinity, I have tried to calculate, it is 60.6%. Okay, so whatever it is lost, that would be this particular area. Okay, the area which you can see in gray color. This means if we deploy a fleet of these components, approximately 60% of them will survive past the 10-hour failure. That is the physical significance of this particular calculation. Okay. So after studying this course, you should be in a position to calculate the reliability of parallel components, of series components, as well as if a CDF, PDF, any type of function is given to you, should be in a position to calculate the reliability. Okay. Now try to solve next question. Okay. Next question is just the repetition of the week one only. It has come from week one only. Okay. The exponential distribution is uniquely defined by a constant hazard rate h of t, which is equal to lambda. Using the fundamental reliability relationship h of t equal to small f of t divided by rt and knowing f of t is given to you, derive the formulas for rt and the PDF f of t. How you will try to approach? Just try to say that. F of t expression has been given to you. Okay. Reliability RT you have to try to calculate and PDF small f of t you have to try to calculate. Okay, do try it. And if you are not able to do, then we will do. Okay, go through the solution, then you will have a better idea. Just try to see here. Okay. See, h of t is equal to lambda. Okay. That has been already given here. H of t hazard rate. Constant hazard rate is there. H of t is equal to lambda. Okay. H of t is defined as small f of t divided by RT. Okay. You try to substitute lambda as minus d by dt of RT divided by RT. Okay. If you will try to just rearrange, then bring dRT here, RT here, and that will be equal to minus lambda dt. Okay. Just we have tried to rearrange this dt here. If you will integrate, you will get natural log of RT equal to minus lambda t plus c. At t equal to 0, reliability is 0. So in this particular case, c is coming as 0. RT is nothing but e to the power minus lambda t. If you try to differentiate it with respect to t, you will get what you will get? Lambda e to the power minus lambda t. And uh, differentiate with respect to time t. Okay. You will get this particular expression. Yeah, you will get lambda e to the power minus lambda t. Okay. So what we want to see here, we want to just say that small f of t, okay, that is coming lambda into the power minus lambda t, means the option would be C. This won't be correct, this won't be correct, this can be correct, okay, and this won't be correct. Okay. So RT, capital RT, what is it? It is coming e to the power minus lambda t. So here it is 1 minus e to the power minus lambda t. So it won't be there. That option is C. What is the physical significance? Hazard rate is constant with respect to lambda. With respect to time, it is constant. Okay. The reliability is always a decreasing function, exponentially decreasing function. Constant hazard rate lambda means the component does not experience a wear and tear. Okay. Its probability of failing in the next second is exactly the same on day one as it was on day 1000. So this describes the useful life phase of an engineered system, means in case of your solid state electronics transistors. Okay. Failures here are entirely random shocks from the environment, not an integral degradation. Okay, that is why you are seeing the reliability continuously dropping as an exponential negative graph. Next is a continuous random variable capital T follows an exponential model. Which of the following equations mathematically defines the memoryless property, proving that a surviving component forgets its past? In which of the expression you can say that it has survived the it is forgetting the past means it is a memoryless model. Okay. So whether it is B, whether it is C, whether it is A or D. This is very simple question. You can very easily solve it. Sir, can you please share integration and differentiation basic formulas which are all using relative means? Okay. In the next week handout, I'll include those also. Basic integration and differentiation formulas. But if you are having any class 12th book, then feel free to go through it. Okay. Basic integration and differentiation formulas, I'll try to provide you. No problem.
Sir, can you please disclose that what is the difference between the differentiation and integration in our real life?
Very interesting question. What is the difference between differentiation and integration in real life? See, By you have asked it, I really appreciate it. Okay, I'm not discouraging you, but by now you should be in a position because I think that you mostly are must be in undergrad. So by the time you are in undergrad, you should be in a position to appreciate what is differentiation and integration, what is the Fourier's interface. Why so? Because after engineering mathematics 1, engineering mathematics 2, and engineering mathematics 3, these are the advanced engineering mathematics. They all are based on this differentiation and integration. And after these three are taught, you must be in a position to appreciate this statistical learning for reliability analysis type of problems. So I'm not discouraging you. Please do ask me. But by now, if you are not in a position to recall the basis, please go through them once. Okay. It is the opportune time for you. Okay. Because what I've seen, whether when it comes to placement or any job interview, you are asked very basic questions like this only. Okay. We'll have to disconnect now due to some other work. Yeah, you please, you can watch it later. No problem. It would be available on YouTube forever. Okay. Yeah. So I'll explain you. No problem. Suppose you are plotting a particular function. Like in this particular case, I have tried to formulate this particular function y square equal to 4ax. So y square equal to 4ax. Okay, this I have tried to plot. Okay. This is the exact parabolic curve of y square equal to 4ax. At the instant, suppose x equal to x1, and there is an instant x equal to x1, and there is another instance at x equal to x2. Okay. So if at x equal to x1, I draw a tangent, and at x equal to x2, I draw another tangent. So tangent to the curve will give me the exact rate at which the particular function y equal to f of x is progressing with respect to x or with respect to t. So that tangent to the curve is nothing but the differentiation, means d by d of something. Okay, d by d of something means the differential rate at which the particular function f of t, f of x, f of y, or f of anything is progressing with respect to the particular variable with which it has been defined. Means with respect to x, it has been defined, means f of x or capital F of x, if it has been defined, then how it is progressing. That is the particular case, particular scenario. Okay. Integration, it means nothing but area under the curve. If I try to calculate this particular area under this curve, that would be nothing but integral of y dx. Okay. That particular value which I am getting after integration is nothing but the area under the curve. And what is area under what this area under the curve exactly denotes means differentiation is nothing but the slope of the line. Okay, slope of the line or the differential rate. Okay, that is nothing but a differentiation. But integration is area under the curve. Area under the curve denotes that exactly with respect to time or with respect to my x, how the change has progressed with respect to your whole span. Means with whole definition, whole of the span of x, how exactly the curve has changed, in which domains it was positive, it was above x, in which domains it was below x, and what exactly the change is there through the entire span in which it is has been defined. In this particular case, if you will try to calculate this particular integral from 0 to infinity, it will come exactly at 0. Why so? Because it's a symmetrical curve. So this portion will be taking as positive, this portion below x-axis will be taking as negative. So the entire area will come as 0. So that is the physical significance of this area under that curve. That is the case of integration, and differentiation is nothing but the slope of the line or the rate of change of this particular thing, this particular function, that is f of s. Yes.
So integration 0 to infinity minus infinity to infinity is there, na, sir, cos to infinity. Okay, but we are using jet value to find out the area of the value it is available.
Mhm.
It is too complicated, like that madam told in the class, to calculate that integration. So that's why we're calculating jet value.
Uh-huh.
So I'm trying to what I understand. That's what I'm telling, sir.
See, variable can be different. It can be z, it can be x, it can be t, it can be anything. But the method will be same only. Okay. I don't exactly understand what you are trying to point it out, but if it is y equal to z cube and y equal to x cube, both will have the same differentiation, that is 3z square and 3x square. So where exactly is the confusion? Please indicate. Okay. Otherwise, if it is clear, then it is fine. Elaborate on your confusion. Then I'll be in a better position to understand. That is what I'm asking you to do. In exam, you will be given virtual calculator. There is a virtual calculator which will be present on the system itself. Okay. In that you will be calculating various values. No. If at all it is required, then you will be using those particular values. Regarding your basic formula, okay, I have given you this particular PDF. This would be there with you in the folder. Google Drive folder is there on this particular link. Feel free to go through it. Okay. All the basic differentiation and integration formulas are there. Okay. So please go through them once, twice, thrice, how many number of times you require them. But do remember them. Okay, these are very handy in your entire engineering course. Not in this particular subject, but as an engineer, you should be knowing this. Okay. Since class 11th and 12th, we are going through these only. Okay, so it is least expected from you. Okay, I shall not be reiterating. Feel free to go through it. And if any confusion is there or you are not recalling, feel free to go through all this. Okay. Then now try to see here. The correct option would be D only. Either you can use B or either you can use C. Both are correct. Okay. Why so? In case of a conditional probability, this was the expression. Conditional probability A over B is nothing but probability A intersection B divided by P. Okay. A is happening at a timestamp t which is greater than s plus t. B is happening at a time interval capital T which is greater than s. Okay. Since s plus t is greater than s and A intersection B is A. Okay. So probability that it would be conditional means probability t greater than s plus t over t over s is nothing but probability t greater than s plus t divided by probability p t greater than s. And in place of your reliability RT, you will, if you try to substitute into the power minus lambda t, okay, you will be getting this particular expression into the power minus lambda s plus t, okay, divided by e to the power minus lambda s. So it would be equal to e to the power minus lambda t. Okay. Since e to the power minus lambda s plus t is nothing but likewise through the exponent property, you can would be able to break it in two different terms. C would be also a fundamentally true, but the condition should be met that the random variable t it should follow an exponential model. If and only if it follows an exponential model, then only your both the options B and C will be true. Okay. Because in this particular case only, it is breaking into two different parts. Okay. E to the power minus lambda s and e to the power minus lambda t. Yeah. That is why in this particular case, both the options would be correct. Okay. A used component is mathematically as good as nil. Okay. If a server hard drive with modeling constant failure has survived as equal to 5 years, the probability it survives another t equal to 2 years is exactly same as brand new hard drive surviving its first 2 years. System has retained no memory for the first 5 years of machine. That is the case here. Now try to calculate mean time to failure of a continuous distribution. It can be derived by integrating the reliability function from 0 to infinity TTF equal to integration 0 to infinity RT dt. Okay. Given an exponentially distributed component with a failure rate lambda equal to 0.002 failures per hour, calculate the mean time to failure. Try to calculate. The given figure showing the distribution of battery lives in the desired area. We need to evaluate the area under a normal curve. To the left of 2.3, this is accomplished by finding the area of to the left corresponding z value. Then we find this. Then using table 1, we have this around one doubt why we need to convert this x to z. Okay. Why you need to convert x to z? Why so? Because in this particular case, we are using z distribution. Okay. That particular uh, probability would only. Okay. Just one second. Sorry, very sorry. My mic got muted. Yeah, in this particular case, the given figure showing distribution of battery lives in the desired area. To find Px less than 2.3, we need to evaluate the area under curve to the left of 2.3, but you need to convert it to the corresponding z value because this p or because this x follows a z distribution that is already embedded in the question. Means this x is following z distribution with a mean mu and a variance that is sigma square. Okay. That is the case. That is why you are always converting the corresponding value from X to Z. Okay. That is the case here. And you have to do this particular thing in all of the cases. If it is a Z distribution, you have to convert it into Z. If it is a P distribution, you have to convert it into that. Exponential, convert into that. Then only calculate the value, operate the function. Okay. हाँ अभी मैं क्लास ले रहा हूँ मैं बाद में कॉल करता हूँ हाँ हाँ बिल्कुल ठीक है हाँ 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 बिल्कुल लेकिन मैं कर रहा हूँ एक पेपर करके अभी थोड़ी देर में तुमको कर रहा हूँ क्लास शुरू हो ठीक है ओके yeah Z table will be given in the examination just yeah Z table will be given in the examination okay no need to worry Z table Key table and all the tables, requisite all the tables will be given in the examination. Okay. So there is no doubt regarding it. Without the Z table, you won't be able to solve it. So don't worry about that. It will be given in the examination. Yes. Now you try to see here, okay, mean time to failure of a continuous distribution can be derived using the reliability function from 0 to infinity. Mean time to failure is nothing but definite integral 0 to infinity, capital RT dt. Okay, lambda has been given to you and mean time to failure has been asked. Okay, mean time to failure is nothing but 0 to infinity, definite integral RT capital RT dt. Okay, you see here that you have been given exponential distribution. So by now, this particular expression reliability in case of the exponential distribution is nothing but e to the power minus lambda t. That should be known to. Okay. If it is known to you, then you will be directly putting this particular value integrating from 0 to infinity e to the power minus lambda t dt e to the power minus lambda t dt. What is the integral? E to the power minus lambda t divided by coefficient of t, that is minus lambda, and you will put the value from 0 to infinity. So e to the power minus infinity is nothing but 0, and minus e to the power minus 0 is 1. So minus 1 by minus lambda. So minus minus is will become plus. It would be 1 by lambda. If you will substitute lambda as what? 0.002 failure per hour, you will get 500 hours. Okay. So reliability curve will try to represent the total expected lifespan of that entire population, total population. That is the meaning of this particular definite integral from 0 to infinity. Okay. So mean time to failure is simply the inverse of hazard rate, that is 1 upon 100. Okay. In practical physics, if 1000 units are tested, they will fail at different times. Okay. The average of all those failure times will mathematically converge to 500 hours. So that is the thing. Mechanical gear system. Next question is this one. The mechanical gear system's failure is modeled by Weibull distribution with a shape factor beta equal to 1.5, scale parameter eta equal to 5000 hours. The hazard rate, hazard function for Weibull function has already been given in the question, that is beta by eta, t by eta raised to the power beta minus 1. Now you have to calculate the instantaneous hazard rate at t equal to 1000 hours. How you will calculate? You will just substitute the value. Okay. Beta is given to you, eta is given to you, t equal to 1000 you have to substitute and tell me what is the correct option which you are given. Okay.
Sir, one small thing,
Yes.
sir. Uh,
Mhm.
Sir, this terminologies beta, gamma, and alpha, these things are there, sir. What we need to understand by seeing these terminologies?
These terminologies have been
I think
derived.
it is a very basic level question.
No, no, you
I know
can
this is very basic level question, but
feel free to ask any
don't know, sir.
basic, any basic level question. Feel free to ask me. Okay. First of all, just go get rid of your hesitation. Okay. Now the thing is, if your basics are not good, it can be a case. Okay, there is no hard and fast rule. So feel free to revise those basics. Okay, from your class 11 books, class 12 books, then your engineering mathematics 1, 2, 3. After all that is covered, then only we are expecting you to take this course, and then you will be in a position to appreciate that what we are trying to resolve mathematically. Okay. This is the primary requirement that your basics should be good. Okay. If it is not good, there is no problem. Just work on your basics. That is what I am suggesting. And regarding what you asked, that what is beta, what is eta, and what you have to just infer from that particular denotions, these are basically used to model the behavior of real-time objects. That is why we have created functions. And functions, we are just trying to complicate those. Why we are trying to complicate those? Because the behavior of the natural things, like the rate of failure of any component, maybe it is a nut, maybe it is a bolt, or any of the component is already complex. Okay. Since the existing phenomena is complex, so we are trying to model it as it is observed in the nature. That is why we have to incorporate these beta, eta, and all of those parameters, A, T, lambda. That is the prima facie requirement. And you need to appreciate the function as well as all its parameters. Okay. Rote learning here, it at some stage is also required to remember the parameters of the basics of the basic functions. Okay. But after a while, when you will be practicing, you will be able to appreciate. When I was in BTech, I was not able to appreciate much of the information. That what exactly we want to infer from a particular function, particular distribution. But now, when I'm in PhD, I have seen things in much greater extent. So I'm able to appreciate that what exactly the inference is there, and I'm able to connect with my practical life. Okay. So bear with it. I have no particular time. I have not been allocated so much time so that I can elaborate on the functions, their principal properties, and why beta, why eta, why not A and B. So that is the case. Okay. But sooner or later in your life, you will be able to appreciate. Okay, even afterwards, in uh, after completing graduation, you would be joining some of the industry, or you would be going to some research. In both of these scenarios, all beta, eta, everything would be there. So sooner or later, with gradual practice only, we generally tend to see that what is the practical significance of beta, eta, A, B, C, D, every parameter in real life. Then only it would be much clearer to you. Okay, when it comes to practical applicability. But uh, my sincere advice is practice. Practice will only make you realize, okay, make you excel in this particular domain. Then only you will be able to appreciate what is the fundamental query which we are trying to solve. Okay. So in this particular case, the variable hazard function already given to you, t equal to 1000 has been given to you. You just have to calculate the value. So putting all the parameters, beta is 1.5, eta is given as 5000, t is given as 1000. Just calculate h 1000 and it is coming as 0.000124 failures per hour. That is option number A. Okay. In calculation, it is this one, but in practical significance, that shape parameter beta defines the component's physics. Okay. If beta is less than 1, then it is early infant mortality, means you require improving your design, require significant improvement in your design. If beta is equal to 1, then it is a constant hazard rate. Okay, means it is exponentially increasing. Okay, or decreasing. Beta is greater than when 1, then it's a wear out phase, means you have to go for component replacement. Since beta was 1.5, the physical significance which we can arrive is that gear is aging. Its hazard rate is strictly increasing over time due to material fatigue, friction, and mechanical wear. Use all the parameters. This beta y for less than 1, it is early infant mortality. Y for beta equal to 1. These limiting conditions we have been derived on the basis of experiments. Okay, experiments which are conducted by engineers, you people only. And on the basis of those conditions only, it is desired or it is projected that at which time, with which particular time, failure would occur. Okay. Now you try to solve this particular question. An I-beam has a structural strength Y distributed as normal distribution with mean mu and sigma. This okay, megapascal. Then applied physical stress X is distributed as normal distribution N with mean 320 and variance 20 whole square megapascal. Then assuming stress and strength are independent, what is the exact probability or reliability for this mean? And you just know that margin M is nothing but it is equal to Y minus X. Okay. The system is safe when capital M or margin M is greater than 0. Try to define. Just try to calculate. Now you try to say here the margin M is nothing but capital Y minus capital X. Okay. Mean of capital M would be nothing but mu Y minus mu X. Okay. Means directly means first of all, this is mean of Y. This is mean of X. Sorry, sigma X or sigma Y. Symbol is Y. Okay. This is sigma Y. Sigma Y would be nothing but equal to 3. Mu y would be nothing but equal to 400. Okay, 400. This mean is this one, standard deviation is this one. Then this one is mu x. Mu x is 320. Okay, and sigma y is nothing but 20. Okay, now you try to see that mean of m would be nothing but mu y minus mu x because directly m has been given in the expression. So 400 minus 320, if you try to calculate, it is 80. Then variance of m is nothing but the sum of both of the variances. Okay. So both of the variances means 30 square plus 20 whole square. Okay, that is 1300. So standard deviation would be equal to nothing but 36.04 under root of 1300. Okay, z if you value if I try to calculate z would be nothing but what mu sigma minus mu divided by sigma. Okay, so this particular m for m equal to 0 x minus mu divided by sigma. Okay, that is the expression of z. So from here, x has been given as 0, mu m I have calculated as 80, and sigma m is coming by 36.05. So minus 80 by 36.05 is minus 2.22. Okay. So if you will try to look in the z table, so p of z greater than minus 0.22 is 0.9868. From z table, you will get it as this particular value. Otherwise, for solving this particular question, just calculating the z value is more than sufficient because z is minus 2.22 in only one of the option. So directly you will take as option B. It is coming 0.9868. Means you try to transform the two interacting variables into a single margin of safety distribution. The variance of the margin adds to the variance of both stress and strain together. Even with a higher average strength 400 versus 320, the unpredictability or the variance in both of the material manufacturing and physical loads creates a 1.32% chance that the weak beam meets up weak load and snaps. Okay. That is the physical significance which we are able to define. Now, next question. In reliability engineering, the log normal distribution is heavily used to model MTTR, mean time to repair, and material fatigue wear process like crack propagation. Mathematically and physically, why is the log normal distribution chosen over the normal distribution for these specific purposes? Why is it so? Four options are there. Please give your opinions quickly. You will see it. Why is it so? It is so because C would be correct. It is bound at 0, no negative times, and is heavily right skewed, capturing the reality of occasional nightmare repairs. Okay, that is the correct option. Why is it so? Because if you will try to see, X follows a normal distribution with variance with mean mu and variance sigma square. T is exponential of X. Follows a log normal distribution because exponential X is always positive for all capital T belonging to 0 to infinity. Unlike the normal distribution, log normal distribution is principally asymmetric, means it is right skewed. Mean is greater than median. It is greater than mode. You must have read it in statistics. Okay. Long right tail stretches towards infinity means normal distribution allows for negative values, which is physically impossible for the repairman. Means t cannot be negative. That is why you are trying to take the log normal distribution. Maintenance tasks are always asymmetrical. Standard server reboot may take 5 minutes. Stripped through or corrupted database done a 5 minute job in 5 hour nightmare. That is why the curve is really right speed. And it is not negative. That is why we are taking the log normal distribution. Okay. Consider the two exponentially distributed components with hazard rate lambda 1 and lambda 2. Then if we assemble these components into a series system, what is the resulting system hazard and how does it behave? By now, you should be in a position to appreciate that what shall be the correct option. It would be only B. Okay. In case of your series, the hazard rate would be staying constant. It would be sum of both the values. Yes, in case of your series architecture, while your reliability would be multiplication of both the values. That is exponential minus lambda 1 t into exponential minus lambda 2 t. That is nothing but exponential of in negative minus lambda 1 plus lambda 2 t. Okay. In case of your parallel architecture, it's minimum of lambda 1 or lambda 2. It's a non-constant function. It is minimum of lambda 1 and lambda 2 and the system reliability would be 1 minus in braces 1 minus r1 multiplied by 1 minus r2. Okay. So here it's the weakest link. Any single failure breaks the system. Adding components strictly increases the hazard rate. In this particular case, both the system fail and to break. Both the system must fail to break the system. That already we have seen in series and parallel combination. Okay. Next is the cumulative hazard rate HT represents the total accumulated risk of failure up to time t and it relates to reliability via RT is exponential minus h of t. So if the component's reliability is given as RT equal to e to the power minus 0.01 t square, what is the instantaneous hazard rate? It is nothing but the differentiation of this particular value. Okay. So fundamentally, RT is e to the power minus h of t. Okay, e to the power minus h of t. RT is nothing but e to the power minus h of t. So if you will take the natural log both the sides, you will be able to obtain this h of t. Sorry, I was a bit wrong here. You have to proceed like this. RT is nothing but exponential minus h of t. Then if you will try to take natural log here, in place of differentiation, you have to take natural log. Log RT would be nothing but equal to minus h of t. So h of t would be nothing but minus natural log RT. So minus natural log e to the power minus 0.01 t square using property of log. This is nothing but negative of log of just 1 second. Negative of log of exponential minus 0.01 t square. So by using the properties of natural log, this will cancel out each other, and this negative will be cancelled out by this negative sign. It would be 0.01 t square. Now, instantaneous hazard rate is just defined by the differentiation of this particular value. That is ht. Small ht is nothing but d by dt of capital HT. That is differential of 0.01 t square. That is 0.02 t. Okay. Capital HT is the area under the curve of hazard, area under the hazard curve. Its mathematical counter of total wear, taking its derivative gives you the instantaneous rate of failure. HT. Okay. Small ht. So instantaneous rate of failure, that is HT, will be equal to 0.02 t. It increases linearly over time. In reliability engineering, this is specific behavior is a subset of the Weibull distribution, also known as Rayleigh distribution, commonly used for modeling mechanically increasing or linearly increasing gain. So here it would be 0.023. Now the final question is this particular one. The critical safety system utilizes 2 out of 3 redundancy architecture. The system works if 2 out of 3 identical parallel components survive up to t equal to 100 hours. Okay, continuous reliability of each individual component at t equal to 100 is calculated to be R100 equal to 0.90. Using your discrete binomial logic, calculate the exact overall system reliability at equal to 100. How you will proceed? X is number of surviving components. X will follow a binomial distribution with n equal to 3. Because 3, at least 2 out of 3 components have to survive. So n is 3 here. Probability is given as 0.90 of the survival. So x equal to 2, probability at x equal to 2 would be nothing but ncx, then p raised to power ncr, p raised to power r, q raised to power n minus r. That is the general expression. So using the general expression, p at x equal to 2, you will try to calculate. Okay. If x is greater than equal to 2, then only the then the system would be safe. So P at x equal to 2 you will be calculating, P at x equal to 3 you will be calculating using the expression which I told you, NCR P raised to power R Q raised to power n minus R. And n we have identified P is 0.9, then Q is nothing but 1 minus P, that is 0.1. Okay. So NCR P raised to power R Q raised to power n minus R, and you try to calculate P2, then you try to calculate P3, then you sum both of those values, that would be coming as 97.2%. Okay. So hazard rate H of t with respect to time t, if you will try to plot, then in phase 1 it would be infant mortality phase, in phase 3 it would be wear out phase, phase 2 will be only your useful event. This marks the end of the 10 questions which I wanted to discuss. Okay, thank you all once again for joining the session. Do join the session next week, same time, same link. Okay, if you are having any confusions, feel free to contact me. Okay, anytime. I will also give my mail ID to you also. Okay. Okay. So, all the very best. We do revise all these things. I'll be putting in the Google Drive folder. Okay. And thank you once again for joining the session. Do join the session next week, same time, same link. And please revise. I'll share this particular PDF also with the basic formula as well as this PDF as well as this particular one. Revise it. After revision only, you will get the confidence in order to excel in the examination. Thank you so much and all the very best. Thank you. And do join the session next week, same time, same link. Okay. And bye. Have a great day. Minding the meeting for you all guys. Thank you.